Okay, so today we're going to derive relationship between E, modulus of elasticity, G, modulus of elasticity and shear, or modulus of elasticity, or modulus of rigidity, and mu, the Poisson ratio. So approach is based on considering an element subjected to pure shear stresses, tau xy, and finding epsilon max by two different ways. So we will see which two ways, and then we'll relate the two results. So the first approach is, the first way is to first perform stress transformation and then use generalized Hooke's law. What I mean by that is, consider this element, and so if you consider it, let's start doing it. You will see that sigma x is equal to 0, sigma y is equal to 0, and tau xy is equal to just any value, tau xy, whatever it is. And if you start finding sigma max and sigma min, you will be able to find it by any method, Morse circle or direct equation. You can find it by any way. So you see that it is equal to sigma x plus sigma y by 2 plus for max and minus for min times sigma x minus sigma y by 2 whole square plus tau xy square. Now since these two values are 0, you can see that this term will disappear and this term inside the bracket will also disappear. This will also disappear, and the only thing you would have would be plus minus tau xy. So it means sigma max would be equal to tau xy and sigma min would be equal to minus tau xy. Just a minute, I'm going to plug my laptop charger. Thank you. न्यूमरेटर में क्या है और डिनोमिनेटर में क्या है? I just cannot recall. Just a minute. Stress transformation. Tau xy divided by sigma x minus sigma y by 2. We can copy this down, take to this. Alright, so this would become equal to tau xy divided by 0. So this will become equal to, approaches infinity, and that means that 2 theta p is equal to 90 degree, and that means theta p would be equal to 45 degree. If you want to find other roots, you can also, you can also write it like this, plus 90, 180 degree, and so this would be 45 and 135 degrees. Alright, so theta p is equal to 45 degree and 135 degree, and then you can, if you like, you can confirm from the general expression for sigma x prime. I know this is simple enough, shouldn't be any problem. If you use this expression, if you copy it and paste it over here, and you can easily see. Alright, so it is equal to, this term is 0, this term is also 0, because sigma x and sigma y are 0, and if you put for theta over here 45 degree, you will be getting from this sine 90 degree is 1, so you will be ending up with, so sigma x prime at theta equal to 45 degree is equal to tau xy plus tau xy. This is what I wanted to see when I put 45 degree in this expression, whether I get plus tau xy or minus tau xy. So you get plus tau xy, and if you just want to see if we had substituted over here 135 degree, it would have been 2 times 135 degree, which means 270 degree, and sine 270 degree would have been minus 1, and you would have got minus over here. But in this case, it is, plus tau xy. So It means at 45 degree we have our, you can see, look at this element at this angle 45 degree, the stress is plus tau xy, which means it is tensile, and at this angle at 135 degree, at this angle 135 degree, it is compressive tau xy. It's same magnitude, but one is tensile and the other is compressive. Well, when you're writing it, when you're showing a compressive arrow like this, compressive by showing it by this arrow, you do not need to write any plus or minus sign. You don't even need to write sigma min or minus max. But just if you want to mention that this is a min and this is the maximum one, you may like to have something written like this. But when you are writing it, you can write with a negative sign, minus tau xy. But when you're showing it, that minus sign only means that it is compressive. When you're showing it compressive, you can simply write tau xy over here. But if you want to write it in an equation, you have to write it like this with a negative sign, because an equation standing alone, an equation relies on this plus or minus sign to tell you the sense of this stress. So anyways, so we have found the principal stresses sigma max and sigma min. And now if we wanted to find strain in this direction, in the direction of sigma max, which we would be calling as epsilon max, by using generalized Hooke's law, then if you have watched the premier that I just shared today, the strain in any direction would be equal to, may I write it like this, any direction would be equal to 1 over e times stress in the same direction as this strain you wanted to find, which is, you know, in the, let's just write same direction, sigma in the same direction, minus nu times sigma in the perpendicular, in the one in one perpendicular direction, and then nu times sigma in the other perpendicular direction. If you recall, this was the expression for epsilon x equal to 1 over e times sigma x minus nu times sigma y minus nu times sigma z. So the general form would be like this. This is in terms of x, y, and z directions, but for any set of 3 directions, you can write the generalized Hooke's law in this format. So we are finding epsilon max at this time equal to 1 over e times the stress in the same direction as this strain. It is sigma max, the major principal stress, minus nu times the other the strain in the other direction, this direction. Let me show you this direction, sigma min. So minus nu times sigma min, all right, minus nu times the other. Look, we have sigma x and sigma min present in this plane, and what about the stress in the out of plane direction? It is 0. It was 0 over here, sigma z, and the out of plane stress is 0 in this case as well. So it remains 0. Sometimes we call it sigma intermediate, something that lies between sigma max and sigma min. Sigma max is a positive quantity here, and sigma min is a negative quantity over here, and sigma intermediate, the stress in the direction perpendicular to the plane, is also sometimes called sigma intermediate. Alright, now in this particular case, this value is tau max, tau xy. If you look at this equation, we have just found this. Sigma max was tau xy, sigma min is minus tau xy, and what about this? 0. So epsilon max becomes 1 over e times tau xy minus nu times minus tau xy minus 0. So this becomes 1 over e times tau xy plus nu tau xy, or we can say 1 over E times 1 plus mu, or you can say just tau xy over here, taken common from this expression, epsilon max. So this is the first way to find epsilon max. This is the first way. Call it equation number 1. So as we said, in this case we first perform stress transformation, and this was the first step, stress transformation, all the way down up to this step, this step. Up to this step we have performed stress transformation, and after that over here we have used generalized Hooke's law. So this is how we this was the route that we took in this case. This was the first way of finding major principal strain, epsilon max. The second way is, let's look at the second way. First use generalized Hooke's law and then use strain transformation. So let's see how this method works. Calculate normal strains epsilon x and epsilon y and shear strain by using generalized Hooke's law. So let's do this first. If you look at this element, you can see that sigma x, sigma y and sigma x, sigma y are 0, and tau xy is equal to any value tau xy. So if we just copy this information down, if these are the stresses that are applied, and not mentioned although in the figure, but we know that sigma z is 0. So with this information we can calculate epsilon x and epsilon y by using generalized Hooke's law. It says this equation, sigma minus nu times sigma y minus nu times sigma z. So in this particular case, this is, all these are equal to 0. Agree? So now we can say that it is equal to 0. Same goes for epsilon y, equal to 0. But just to tell you what expression would it be, equal to sigma y minus nu sigma x minus nu times sigma z, equal to 0. Why? Because all these stresses are equal to 0. So it means epsilon x is 0 and epsilon y is also 0. And what about the other strain, tau xy, gamma xy, gamma xy is equal to tau xy over g. This is what we have seen in this lecture. All right, this is what we have seen in this lecture. Look at this. So we can write it just as it is, because tau xy is just tau xy. In this case we have given it same name, tau xy, and g is, g will remain g. We can't do anything about this. So we have found epsilon x, epsilon y and tau xy. So here is the summary. We have found that epsilon x is equal to 0, epsilon y is equal to 0, and gamma xy is equal to, any value, just gamma xy, call it gamma xy. If you want to write it in this form, you can write, but we will do this substitution at a later stage. But now this was the first step in this process, in this route, second method, generalized Hooke's law. First use generalized Hooke's law. We have used generalized Hooke's law to go from stresses to strains, and now we will perform strain transformation in order to find epsilon max. All right, epsilon max. Now you should be able to do this. Epsilon max would be equal to epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2 whole square plus gamma x y by 2 whole square. Is this right? Now in this particular case you can see that these two terms are 0, epsilon x and epsilon y are 0, so this will disappear, and same goes for this one, and we can write it equal to gamma xy by 2. Now gamma xy, as I mentioned, is given by this expression, related with tau xy by this expression. So we can say epsilon max is equal to tau xy over 2g. If you put the value of gamma xy from this expression, you will be able to find, to reach this expression. Now this was the second method. We have applied the second method also, and we have got this expression, epsilon max equal to tau xy divided by 2g. Now this was the second way, call it equation number 2. Now if you look at equation number 1, epsilon max equal to this by first method and epsilon max equal to this by second method, we can relate. We can see that it means this right hand side is equal to this right hand side, because both equations have same left hand side. So it means tau xy by e into 1 plus nu tau xy by e times 1 plus nu, this comes from equation number 1, is equal to tau xy over 2g. This comes from the second equation. So now you can see that tau xy is common for both sides, so we can knock it out and we will be left with 1 plus nu over e equal to 1 over 2g. Now you can write it in either way you like, but it is often written as I can write it as 2g times 1 plus nu equal to e, and then I can rewrite it as maybe g equal to something, if e divided by 2 times 1 plus nu. This is a relationship between the parameters that we wanted. This is the end result. The relationship between E, G and nu. So for an isotropic material, for isotropic and homogeneous material, we can, if we know one of these, if we know 2 of these 3, we can find the other one. Often you will you use these expressions in a different kind of situation. Often this one is easy to determine because it's related to axial type of loading, and this is also not very difficult to find, but this will require you to perform a pure shear or a torsion type test, which is not so common. So this is often determined by using E and nu, but in any case you can relate it, you can use it, this expression in any way you like. G equal to E divided by 2 times 1 plus nu. These keep in mind, G, E and nu are all material properties, so this is a material property relationship. All right, so let me know if you have any question on this.